The next question is, what happens if those aren't perpendicular? But what if the force vector isn't perpendicular to the line between P and A? Well, it turns out that you can, without changing the problem, so without changing anything about the problem, you can move the force anywhere along what's called its line of action. Okay, so if this is some random object and this is the force, okay, so the force is acting at this point P, but you can treat it like that force is acting anywhere along this line, a line that goes through that point P and is parallel to the force vector. So if the force vector isn't perpendicular to the line between P and A, just move P along that line of action until they are perpendicular. Any questions about that? I'll do an example. The units for moment or torque are a force times a length. You can see that just from the definition of what a torque is. You take a force and you multiply it by a distance. And so the SI units are newtons times meters. We've actually seen a unit, a quantity that was newtons times meters before. Do you remember what that was? What we used that for? What? Yeah, right. Any kind of energy. So any kind of energy has units of newtons times meters. With energy, though, we call a newton times a meter a joule. Even though we could call this a joule, we call this a Newton meter so that we don't get confused and think that it's energy, you know? Don't call this a joule. It's not a type of energy. Okay, let's do an example. Okay, so let's say we have, okay, let's say this is a football player. We can only deal with rectangles though, so he has to be a rectangular football player. Okay. Okay, so that's a football player. And let's say that mass is what, 100 kilograms. And we're going to treat it like the axis of rotation. So how do I want to do this? Well, let's say he's on the ground. And so the axis of rotation is going to be right here on the ground. Okay. And let's say that a defensive player, oh, we need to give dimensions here. So let's say this is 0.3 meters, and let's say that's 0.5 meters, and that's 2 meters. Okay. And let's say a defensive player comes in on this side. Let's see. Okay, so a defensive player comes in over here and applies a force of, what's a good football force? I have no idea. 1,000 newtons. So that's supposed to be like at the middle of the height, 1 meter off the ground. And then another player comes in and my chair just broke on the last day of class. And another player comes in and, headhunts him, or you're not allowed to do that. If any of you are football players, that's an illegal play. But so one person comes in, boom, hits like on this side, medium high. This one comes in and hits right at the top of the head. And we want to figure out what the angular acceleration of this football player is going to be. Okay? Well, the first thing we have to do is think about what all the forces are. So, free body diagram. What forces are acting on this football player? Yep, there's a weight of 100 times 9.81, so 981. And then there's a normal force. That's where his feet are in contact with the ground, so that's going to be just some upward force N acting at that axis A. And then there's 1,000 newtons here and 1,000 newtons here. Well, we have to calculate the mass moment of inertia, and then we have to calculate the moment about A produced by each one of those four forces, and then add them up, and we'll use that angular version of Newton's second law. Okay? Anybody have any questions about what we're trying to do here? Okay, so I guess first I'll calculate the mass moment of inertia. Well, that's one of those three types that we talked about. Which one is it? So there are three possibilities. The axis of rotation is in the center of the rectangle, or it's in the middle of one side and the end of the other side, or it's at the corner. Yeah, so it's going to be 1/12 times 100 times the length, so the 1/12. That's going to be the length where we're in the middle. Okay, so this is 0.5. That was not clear. But anybody have any questions about that? Help me clarify that. Okay, so when you're using that second one, you're going to be in the middle of one length and the end of one length. The one that you're in the middle of, that length goes on the 12. The one that you're on the end of goes on the 3. So then we have 1/3 times 100 times 2 squared. And that is 100 over 48, I think. So 100 over 48 for that first one, plus 400 thirds. Can someone tell me what that is, just as a decimal? What is it? 135.416. Okay. And the units there, kilogram, meter squared. Now we have to figure out the moment for each of these four forces. So what about the normal force? What's the moment produced by the normal force? Well, the way you calculate that moment is it's the force. So it's a force times the distance from the axis to where the force is applied. What's the distance from, so the axis is here, right? The force is also applied there. So what's the distance? 0. So the moment is equal to the force times 0. So there's no moment. That's like the case where you're applying the force to the wrench right above the bolt. You're never going to turn it. So that doesn't do anything to turn it. And now let's think about the weight force. Well, in this case, the distance, remember that the line from the axis to where the force is applied has to be perpendicular to the force vector. And that's not the case right now. The line from A to P is up and down, so it's parallel to this. And so we're going to have to move this weight force along its line of action. And notice that if you move it along its line of action, you can move it right to where it acts at the axis. So any force whose line of action goes through the axis doesn't produce a moment. Okay. So in that case, we have 981 times 0 again equals 0. We just moved P along its line of action. till it was at A. You can't do that with every force, but whenever you can, that force doesn't produce a moment. Okay, and now the middle force, the force applied to the middle. We have a force of 1,000. But notice that if P was here, and this is A, the line between P and A isn't perpendicular to the 100. Okay, so we're going to have to move this force along its line of action. This is its line of action. Okay, so if we move this force until it gets right to the middle, then you can see that this does become so. Let me draw this. So now we'll say the force there. Okay, now the line between P and A is perpendicular to the force. Anybody have any questions about that? And so now we can just take that force, multiply it by the distance, that red line. What's that distance from P to A there? 1, yep. So 1,000 times 1. And then we also have to think about the direction. If this thing can rotate around here, which way would this force make it rotate? Clockwise, so this is negative. So we have a moment produced by that middle force of negative 1,000 Newton meters. And then for the top force, we're going to do the same thing. So instead of applying the force here, we'll move the force along its line of action. There's its line of action until the force vector is perpendicular to that line between A and P. So I'll move it to here. And then the distance is the distance. So this is P. There's the distance we want. And so that moment is equal to the force of 1,000 times what's the distance in this case? 2. And then would this one make it rotate clockwise or counterclockwise? Counterclockwise, so this one's positive. We have positive 2,000 Newton meters. Finally, we can put this into the, angular Newton's second law equation. We add up all of these moments. So 0 plus 0 minus 1,000 plus 2,000 is equal to the mass moment of inertia, 135.416 times the angular acceleration. And so we get positive 1,000 divided by 135.416 is equal to alpha. Can someone divide that? 7.38 radians per second squared. So is that football player going to rotate clockwise or counterclockwise. Yep, this is positive. So yeah, anti-clockwise, counterclockwise. Okay, so I'm going to do an example of using the angular version of Newton's second law. So the equation we're going to use is this. You add up all the moments around the axis. It's equal to the mass moment of inertia times the angular acceleration. So let's say that we have, let's think of this, no, let's do it like this. Here's the wall. And there's a hinge here and a rectangular shape like this with a thickness of 10 centimeters, so 0.10 meters. And a length of 2 meters. And say the mass of this rectangle is 10 kilograms. And someone applies a 50 Newton force here. And we want to know what's the angular acceleration of the object. So first, I'm going to draw a free body diagram. So what are the forces acting on this? There's weight that acts at the center. And that's 10 kilograms times 9.81, so 98.1 newtons down. And then we have 50 newtons acting here. And then over here is the axis, the hinge that it rotates about. That's our axis A. And there's an unknown force vector that's applied to the body by that hinge. You know that since that thing isn't allowed to move, that the hinge has to apply forces to it to hold it in place. We don't know what those are. We could just write it like, I'm going to put it in a funny color because it turns out the forces that act at the axis, you can just leave out of the problem. They never show up in the rotational version of Newton's second law. But I'll write this as Fx and Fy. And then we have to calculate the mass moment of inertia. I gave you 3 ways to calculate the mass moment of inertia for a rectangle. One where it's right at the center, one where it's all the way at one end but in the center on the other side, and one where it's at the corner. This one is at the end, lengthwise, but at the center, height-wise. So the formula we're going to use for this is 1/3 times the mass times, now the dimension where it's at the end is attached to the 1/3, so this is going to be 2 squared. And then 1/12 times 10 times the other dimension, the dimension where it's in the middle, squared. Can you see what I'm talking about? Like, it's at the end of this dimension, so that one is attached to the third. It's at the center of this dimension, so this dimension is attached to the 12th. What? Oh, it should be a 12th. Sorry about that. Well, I'll give you the formula on the test anyways, but yes, there should only be thirds and 12ths. Okay, so this first term is 4, 40 thirds, so that's 13 and a third. The second one is 10 twelfths, 5/6, times 0.1 squared, which is 0.01. So that's a tiny, I think that's plus 0.0083 repeating. This is like 13.3 repeating. And so this is equal to basically 13.34. The units are, you're taking a mass for this formula and multiplying it by a length squared, so it's always kilogram meters squared. And now we have to think about the moments that these forces produce. Okay, so the force vector F, what moment do those forces produce around this axis? Well, they're acting at the axis. And remember that to calculate the moment, you have to have a distance from where the force is applied to the axis. So any force that acts at the axis doesn't produce a moment. Okay? It's like trying to turn a bull with a wrench by pushing down directly on the above the bull. It's not going to ever turn it. So this is 0. And then the weight force, if you draw the line from the axis to where that force is applied, those two are already perpendicular. So we can just calculate this moment as the force, 98.1, times this distance. What's that distance of that green dotted line? Yep. And then we have to think about the direction. If you applied this force and it was the only force applied, would it make it rotate clockwise or counterclockwise? It would make it clockwise, yep. If you applied this 98.1 newtons force there, and the axis is here, this force would make it rotate this way. So it's negative. That's because it's clockwise. So negative 98.1, and the units are newtons times meters. And then we have to do the same thing with that 50 Newton force. If this is applied at the corner, then notice that the line from where the force is applied to the axis isn't quite perpendicular to the force. You see that? If I draw this line, it goes from the corner up to, it's almost perpendicular, but not quite. But you can move this force along its line of action until it's perpendicular. So just imagine this force acting here instead. And then a line between where the force is applied and the axis is perpendicular to the force. And so the moment is 50 times what's the distance from this little blue dot to the axis? 2, yep. And would that force make it rotate clockwise or counterclockwise around A? Counterclockwise, so this one's positive. And so you get positive 100. And now that we've calculated the moments produced by all of those forces, we can put it into this equation. I haven't used that abbreviation before. This is, so put it into that sort of angular form of Newton's second law. So we have 0 minus 98.1 plus 100 is equal to 34, no, what was it, 33.34? 13.34 times alpha. And so positive 1.9 is equal to 13.34 alpha. So what do you get for alpha? .142, and that's radians per second squared. So is that angular acceleration clockwise or counterclockwise? Counterclockwise. So that means that even though this force is almost twice as big as this one, the combined effect of these two is to make this thing start to rotate counterclockwise. And the reason for that is this force is acting a lot farther from the axis than this one is. And so it has more of an advantage in producing the moment. Okay, so this one, let's think of this as like a seesaw. Let's say the axis is right in the middle. The length of the whole thing is 5 meters. And let's say there's a force of 500 newtons acting half a meter from the axis on this side. And a force of 100 newtons at the end on the other side. And the idea is this is connected to the ground. You know, this is like a hinge. So we want to see how this seesaw is going to rotate. We have to give a mass here. Let's say the mass is 30 kilograms. Oh, and I need, that's 5 meters. I need a length here too. Let's say this is 0.2 meters. Okay, so draw a free body diagram. So what forces are acting on this board? There's the 100 Newton force here. There's the weight acting right in the middle. That's 294.3 newtons. There's the unknown force coming from the axis. I'm just going to leave that off, though. I mean, it is a force, but it's not going to produce any moment, so it doesn't matter to us in this problem. Oh, I'll put it on here as like, remember it's there, but it's not going to affect the problem. Okay. No, not for these rotational problems. And then 500 newtons here. So mass moment of inertia. The axis in this case is at the center of that rectangle, so we're just going to use 1/12 times the mass times 5 squared plus 0.2 squared. Can someone calculate that? Oh, 62.6? Okay. And the units are kilogram meter squared. Thank you. And now we'll calculate the moments. So the 100 Newton force. That one's really acting up in the corner. But we can just slide it down until the line between the axis and where the force is applied is perpendicular to the force. Remember what I'm talking about with that? And so the force is 100 newtons. The moment arm is 2.5. So you get 250 Newton meters, and we have to think about the direction. Would that 100 Newton force make it rotate clockwise or counterclockwise around the axis? Counter, yep. And then the weight, that's acting right at the axis. So we have 294.3 times 0, so that's not going to make it rotate. And then the 500 Newton force. Again, the line between the axis and where the force is applied isn't perpendicular to the force. But if we slide the force along its line of action to here, then it is. So what's the... Okay, so we have a force of 500. What's the distance from the axis to that new place where it's applied? 0.5. And would that 500 Newton force make it rotate clockwise or counterclockwise around that axis? Clockwise. So you get negative 250. Ooh, that just, I didn't even think about that, but it ended up coming out exactly the same. Okay, so now we can go to the angular Newton's second law. We'll add up all these moments. So we have 250 plus 0 minus 250 is equal to 62.6 times alpha. And that says 0 is equal to 62.6 alpha. So the angular acceleration is 0. Those two exactly balance each other. And you know that effect from from seesaws, you know, like if a smaller kid sits really far from the axis and an adult sits close to the axis, you can make it balance even though those weights are drastically different. Okay, so let's say the length is 2 meters. The height's 1 meter. The mass is 5 kilograms. Let's say the axis is at the center again. And we'll apply a force to it like this. Let's say this time it's a top-down view. So let's say this force is 200 newtons. What's the angular acceleration? Okay, so free body diagram. We have the force over here of 200. And we have the force here at the axis that we can ignore. It's not going to produce a moment. Since it's a top-down view, the weight is acting into the page, so that's not going to show up in this calculation. The mass moment of inertia is 1/12 times 5 times 2 squared plus 1 squared. So that's 25/12. So 2 and 1/12. .083. Okay, so the only thing that could produce a moment here is this 200 Newton force. But notice that if you draw a line from the axis, so this is the axis here, right? If you draw a line from the axis to where the force is applied, it's not perpendicular to the force. So that's not going to work. So where are we going to have to move that force to along its line of action so that those will be perpendicular? Here's the line of action. Where do we have to move that to so a line from the force to the axis will be perpendicular to the force? Yep, middle. So we'll move it to here. Then we have the force going this way. We'll stop thinking that it's over there and think that it's in the middle. And now the line from the force to the axis is this. It's perpendicular to the force, so now that works. And now you might have thought that the distance we were going to use was this one or something, or this diagonal distance. But it turns out the distance that we're going to use for the moment is just this small distance, half a meter. Yep.
So why can't you move it from
So this dotted line is the line of action. And you can move a force anywhere you want along its line of action. It doesn't even have to be touching the body. You could, if it helped you do the problem, you could move this force out to here. Okay? And it doesn't change anything about the problem. It's just a tool for doing the calculation. Okay, so the moment is 200. So 200 newtons times the distance, the length of that green line, which is 0.5. And now if this thing was free to rotate around A, and you applied this force here, would it rotate clockwise or counterclockwise? Counterclockwise. So this is positive. So we get positive 100 Newton meters. And so the angular Newton's second law says 100 is equal to 2.083 repeating times alpha. So alpha is equal to, can someone divide 100 by 2.083 repeating? 48.007 radians per second squared. So which way is the angular acceleration? Counterclockwise, yep. Okay, so let's say this is, let's say that's 1 meter. And that's 0.1 meters. And here, let's say we apply a force of 200 newtons. And here there's some force F applied. What's F required so that board is, stays at rest? In other words, so the angular acceleration is equal to 0. Well, we have a length here. Let's say the length here is 0.01 meters, 1 centimeter thick. And let's say the mass of the board is 2 kilograms. And let's think of this as like a side view. So there is going to be weight for this board. Okay. A free body diagram. There's a 200 Newton force. there's a downward force at the middle of 2 times 9.81. There's the two forces here that aren't going to affect anything. And then there's a downward force F that we're trying to calculate. And let's wait to, you can do it in any order, but let's wait to calculate the moment of inertia. And, you'll see why when we get to the equation. So the moment produced by the 200 Newton force. The axis is over here. So imagine moving the 200 Newton force down to the middle. Then you have 200 newtons times what's the perpendicular distance to the axis? 1. And would that 200 Newton force make it rotate clockwise or counterclockwise? Counter, yep. And then we have the weight force. How far is it from where the weight's applied to A? Well, that's a little tricky, I guess. The weight acts in the center of that board. So you have to do a little geometry to make this work. The whole board is 1.1 meters long. So the weight is going to act 0.55 meters from the end, right? But this is 0.1 meters. So it's 0.45 meters from here to here. I won't make you do that okay, but it is 0.45. So we have 19.62 times 0.45. Would that weight force make it rotate clockwise or counterclockwise? Counterclockwise. Remember where the axis is. So it would rotate around again here. So if you tap it down, it would rotate this way. Can someone calculate that? Yes. Because, so first I moved the line of action. Got it? Okay. And then the last thing we have is that force F. Again, we have to move that down along its line of action until here. And then what's the distance from this point to the axis? 0.1, yep. And would that force make it rotate clockwise or counterclockwise? That way it would be clockwise, so this is negative. Yes? The 0.001, the 0.01 is just the thickness. The distance we're talking about now is the distance from here to here, and that's 0.1. Okay, so now let's go to the angular Newton's second law equation. I still haven't calculated the moment of inertia, but we're going to see that it doesn't matter. So let's add these up. We have 200 plus 8.829 minus 0.1 F is equal to the moment of inertia times 0, because we're trying to find this F for when the angular acceleration is 0. this all goes away. And you get that 208.829 is equal to 0.1 F. And so F is equal to 2,088.29 newtons. So let's say this is a top view. And let's say the axis is here. And let's say there's a force applied of 100 newtons. This length is 0.2 meters. This length is 0.4 meters. And the mass is 10 kilograms. What's the angular acceleration? All right, so free body diagram. There's the axis, and there's two forces there we don't care about. And then there's a force here of 200 newtons. If you draw a line from the axis to that force, you can see it's not perpendicular to the force. What? Oh. I was going to do a problem that was twice as hard. Okay, so that doesn't work, but we can move this force along its line of action, which is this. I don't know if this helps. You can think of it this way. So you can move this force along here, and imagine that this blue line just keeps moving with the tip of the specter as you move it around. So it's like, and right here, that force is perpendicular to the line between them. Yes. No. If you can do it in your head, that's perfectly fine with me. So we'll take this force and move it down to here. And now the line between the axis and the force is perpendicular to the force. The moment produced by that 100 Newton force is 100 times the length of that blue line, which is 0.4. And if this is the axis, would this force make it rotate clockwise or counterclockwise? Counter, yep. So this is equal to positive 40. And the moment of inertia is, in this case, the axis is at the corner. So the formula is 1/3 times, what did I say the mass was? 10. 1/3 times 10 times 0.4 squared plus 0.2 squared. This is 0.16 plus 0.04. Wow, I got to remember that. That works out nice. 0.22 2/3. And now we can put this into the angular Newton's second law. And we get positive 40 is equal to 2/3 alpha. So alpha is equal to 160 radians per second squared.